Hello, everybody, and welcome to Shop Talk Live, the Aluminum series. My name is Mike Van Helvoort. I'll be your host for this evening, and welcome back to everybody who's been on these Shop Talk Live seminars before, and a great thank you to those who are joining for the first time. Want to say real quickly before we get started, we have a chat function on the live stream, as well as an email if you had any questions during the session tonight. We'll try to get to as many questions as we can. The email is shoptalklive@millerwelds.com. We have a little bit of a severe weather happening right now in the Appleton area, so I apologize if some alarms go off. We've already been through it once, but we're trying to push through this weather to get this thing out to everybody in tonight's audience. All right, let's get going to it. All right, tonight we're back with Andrew, and he's going to walk us through some advanced TIG tips. Over the course of the past few weeks, he's walked us through the basics and kind of intermediate tips of TIG welding on aluminum. Tonight he'll dive a little deeper into some of the things like independent AC settings, gas types and gas flow rates, welding aluminum and DC, and then anodized aluminum as well. But first, Andrew, would you mind giving us a quick recap of what we covered last week?
Yeah, sure, Mike. So thank you for the introduction. What we want to go through, or what we talked about last week, we talked about a couple of what we kind of consider the intermediate concepts. And those are going to be our balance, our frequency, our different wave shapes, as well as the tungsten. So just kind of in recap here, I have the notes down here. And so we talked about the tungsten types was the first topic that we covered. And with pure tungsten, that tends to ball back because it has a lower melting temperature. And when we go through and utilize either a 2% seriated or 2% lanthanated tungsten, that gives us the ability to maintain a more pointed tungsten with an inverter-based power source. And that can have some effects that benefit anybody doing welding on aluminum, because in the AC waveform we tend to have a little bit of arc wander, and so using some of these things that we talked about in conjunction with each other, you can actually help focus the arc a little bit better underneath where the torch is pointed, and that helps get the operator able to accomplish that weld a little bit easier. If we go to the next thing that we covered last week, which was the balance setting, so these were some of the diagrams that we drew, and we talked about where the heat is in the different polarities. In electrode negative, a good portion of your heat is being generated in the work, and electrode positive, a good portion of the heat is being generated up into your tungsten, and so that can have an effect, as you can see here, on the shape of your tungsten. If you skew this more towards the electrode positive side, then you end up with more heat on the tungsten that causes that balling shape that can affect your ability as a welder to get the arc to go where you want it in like a fillet weld application. And then if you skew it more towards the electrode negative side, giving yourself more time, you're reducing the cleaning action. It's going to pull heat off of the tungsten, allow you to utilize a more pointed tungsten. But one of the downsides to that is you can get that black peppering in the welds as a result of the oxides and the lack of oxide removal during that portion of the weld. The next topic that we did talk about was the actual AC frequency. So when we have electrode positive and electrode negative, we're not changing the ratio. You can see the areas that we drew here showing that the area remained the same. We're just changing polarities twice as fast in, for example, 120 hertz versus 60 hertz. And some of our equipment goes up to 400 hertz on AC. And the big benefit there is it helps us drive the arc right down into the bottom of like a fillet weld and prevents that arc wander. Many codes and specs, which we'll talk about briefly here, require us to consume that root of that joint in order to be considered an acceptable weld, either for qualification and or for production. The secondary impact that is useful for the viewers is the weld size. If you struggle to get a weld and get it in the correct location, you may be putting extra heat into the part. which means you're probably throwing more filler metal into that weld joint. And so we did talk briefly about the impact of, you know, the cross-sectional area, the amount of distortion that can happen in the part, which, you know, leads to rework on the backside of a component, as well as the direct cost as far as filler metals into that welded component by over welding something compared to what it was designed for, and the added weight that that can have on the structure. And so the general recommendations there were, if you're doing thicker applications, you know, high amperage or overlay applications, you're probably going to be using a lower frequency, like 60, 70 to 90 hertz. And if you're doing higher frequencies, that's probably going to be used more on a, you know, thin materials, low amperage applications where you don't have that arc column stiffness from the amperage, and inside corners are an excellent place to be using that, you know, 120 and up, and my recommendation is up to about 250 hertz for handheld applications. And then the last topic that we covered last week was the different AC waveforms. So again, amperage drives penetration for us. So all of them get you, you know, roughly the same peak if you're doing, you know, thinner materials, but the impact that that can have as far as heat input into your part. So the triangular waveform, just for those that maybe didn't watch the video or the live stream last week, what we talked about is heat essentially equals area underneath the curve. So in a triangular waveform, or this blue area here, what you have is you're still getting the peak to drive penetration, typically used on thin materials. And the reason why we do that is because you can see, as compared to like one of the green boxes here, it's about half of the area, so about half of the part being generated in the circuit. And so we're taking, in essence, a majority of the heat out while still getting the penetration that we need on thin materials. Now, when we look at like a sinusoidal waveform here, the sinusoidal waveform, which was common on traditional equipment, or what was generated on traditional equipment, gives you a little bit more heat. We still have options in the power sources for that, but the most commonly used is going to be the green square, or the advanced square that's drawn on the paper here, or my personal preference, which is where we round those corners off, gives you that soft square waveform, and that's good for, you know, 1/8 inch up through about 3/8 of an inch or so materials, and gives you excellent results with that.
Great.
So that's just a quick overview of kind of what we talked about last week. I know we had you know, some issues on the original live stream with the audio, and so there was maybe some viewers that missed out on catching some of that content, or maybe didn't get to see the recording that we did and sent back out.
Perfect. All right. Appreciate that, Andrew. Hey, you mentioned something in your open here about specs and codes. And before we get into more advanced features of TIG, I know you're involved in the AWS and have experience with crafting some of those codes and specs. What do you want our audience to know before they start playing around with some of the more advanced features of TIG welding about codes and specs?
Yeah, certainly. So one of the things that I think is very important whenever we're looking at the weld settings and trying to get different effects using the different parameters that we've talked about, both, you know, the past basic and intermediate, as well as the, you know, particularly some of the topics that we're talking about tonight, is whether it's a machine setting, you know, balance, frequency, the waveform, or gas settings, you know, anything that goes into the setup of the weld. What we need to be mindful of is that many of the codes and specifications that, you know, provide some governance around the welding parameters and the welding process, in many cases, those parameters may be considered what's called an essential variable. And what an essential variable is, when we go through and we qualify a weld, or put together the recipe and prove that that recipe makes an acceptable weld, if we go changing the different ingredients that go into that, that can impact the outcome. So it's like, if you think about baking, you're trying to bake a cake and you use, you know, sugar. If you substitute sugar for salt, you're not going to get the same result, and you're not going to likely like the result. So we want to be mindful of what is required by the codes and specifications that we're trying to weld to, and definitely stay within the bounds that are put forth by those to make sure that any changes that we do are allowed, or we're doing the appropriate qualifications if we do make changes that are outside of the allowables.
Yeah, got it. So in previous sessions and in kind of the recap prior to this one, you mentioned things about electrode positive and electrode negative, but more in relation to kind of the cleaning action for AC welding. I know there are other things that are important about EN and EP. Can you explain a few of those?
Definitely. So I think what we're going to want to do is we're going to want to draw some diagrams here. So as we talked about last week, electrode positive and electrode negative in terms of balance, or the amount of time that we're in one polarity versus the other. So if we draw a waveform here, and I'm going to just draw a square waveform, and I'm going to just for ease of drawing, I'm going to do this at a 50-50 balance setting. And so for the viewers that are watching here, we have our electrode positive time and our electrode negative time, and I'm not drawing it skewed to 75% balance, but I think this helps represent for people. The electrode positive, as we talked about, puts about 70% of heat up on the tungsten. And then this is roughly 70% of the heat on the workpiece. And when we think about one of the topics that I covered last week is that amperage drives penetration. And so if we are trying to achieve more penetration, we can turn our amperage level up. However, if we do that both in electrode positive and in electrode negative, what ends up happening is we're putting more heat into not only the workpiece, but we're also putting more heat on the tungsten. And one of the things that we drew and just covered briefly this tonight yet is that can have a negative impact on our tungsten. By more heat on the tungsten, it means more of a bald effect. So what we can do is, if we have adequate cleaning action, we know that just a rough number is about 80 amps is where we start really getting good, adequate cleaning action. But we don't want to skew too far, from each other as far as, and I'll talk about some of the ratios. But we want to make sure that we get adequate cleaning, but we can also start adding extra heat. So if you think about, we pump extra heat down here into our work without adding extra heat up onto the tungsten, maybe we say, you know what, we're not gonna add that extra heat up onto the tungsten. We're gonna leave this at, let's say, 100 amps, and we might turn our electrode negative to 150 amps. That is going to allow us to use a smaller diameter tungsten in order to accomplish the weld, but not end up with that balling effect. So the benefit of using electrode negative is we can increase that amperage in the workpiece, or that the heat down into the workpiece. Not in relationship to time, but in relationship of amplitude or magnitude, to get us that extra penetration, because amperage is what we know drives penetration, while limiting the amount of heat on the tungsten in the cleaning action. And that's going to be critical to, if once you start getting above, let's say, 200 or 300 amps, in particular, you probably want to start skewing your independent amperage or your ratios, so that way you don't have excess heat on the tungsten. And the rule of thumb that we generally recommend is your EN to EP ratio is going to be about a 1.5 to 1 or up to a 2 to 1 ratio. And what that's going to do for us, like I said, it's going to give us extra heat down into the workpiece while reducing the heat in the tungsten. We're still going to use our balance settings accordingly to look for that black peppering like we talked about last week. But this is a great way to not only stretch the machine, get a little bit more heat into the workpiece, and stretch the consumables a little bit further than maybe what we could have in the past. Start slowing down that tungsten erosion, and also it's going to have an impact on the penetration profile for sure. Now, what we don't want to do, or I wouldn't necessarily go so far as to say we don't want to do it, because there's probably an application that I'm not aware of that somebody may be doing this, but we wouldn't necessarily want to do a ratio like a 1:2, where we have more electrode positive, because what that's going to do is that's going to give a significant amount of heat up onto this tungsten and definitely cause a balling effect during the weld that could lead to tungsten erosion and ultimately tungsten inclusions in the weld, which would lead to welding discontinuities. And according to many codes and specs, those tungsten inclusions would be rejections during some sort of an X-ray process. So what I would like to cover, I know many of the users and the past comments of the past sessions want to know, okay, we talk about all these great features. Let's see actually how to implement them or set them on the welder. So the machine that we have here tonight is the Dynasty 280, and we did put, this doesn't have the independent amperage built into the product. The Dynasty 400 and 800 products do, but we do have an expansion memory card that allows us to access that or adds that functionality into the machine. And so it's simply just an SD card that we put into the SD card port, and that activates or puts the software into the machine. And so the way to access that independent amperage and set it according to what we talked about here is using our AC wave shape button. So just like we would get into balance and get into frequency, once that card is in there, now you can see here it gives us our electrode negative amperage and tells us our waveform. So we're going to talk about waveform a little bit as well. So electrode negative, now remember we talked about the ratios. So the 2:1 or the 1.5:1 ratio, we're going to adjust our electrode negative, for example, to 200 amps. And our electrode positive, we're going to turn down to 100 amps. And what this is going to do for us is this sets our ratio. So now if I go back to my main screen, I have our balance setting. I'll just click into it for us. Our balance setting is at 75%. Our frequency is at 120 hertz. Our balance setting is going to impact our average amperage that's displayed on the front here. So a 2:1 ratio, you think, well, you're going to get at a 50-50 balance, you're going to get an average of those, which would be 150 amps. But because our balance setting is set at 75%, we're getting more electrode negative, which is that higher amperage, which is why we're getting a higher number here. Now, let's say as a user, I don't need 175 amps. One of the ways we can overcome that is using our foot pedal and just throttling it. But if we know that we're going to need either a higher or a lower setting, we can simply turn this number down to whatever amperage we need and get that same ratio. And the machine in the background is automatically going to keep our EN and our EP ratio where we set it, so that 2:1 ratio. We talked about waveforms last week, utilizing different waveforms, and we touched on it briefly at the beginning of the session tonight, the different waveforms. You can adjust the waveforms independently when you have this feature added into the product. And again, as we talked last week, use the amp and the gas dig button. And then we're going to use the gas dig button to scroll through until we see waveform. So here it says AC EN, or AC electrode negative, is a soft square. We can change this to maybe like an advanced square waveform. And then we hit the A button. Now it's AC electrode positive, and we can change this to maybe like a triangular waveform. So again, that's going to give us those peaks in electrode positive to do the cleaning action, but significantly reducing the amount of heat overall into the system. And again, the heat in the system in electrode positive, a large portion of that is being generated on the tungsten. So this is another factor that can help us impact our tungsten life. it can have, depending on how far you skew these and where you have these things set, you may have to be careful because the welding characteristics may and can become, undesirable if you skew them too far and start getting some really crazy combinations. But kind of using the guidance that we talk about and understanding the theory behind it, which is really why we're here tonight, can help you make good decisions on setting your product and setting it appropriately for your application. So now that we have that set, we just hit the amp and the gas dig button, and that takes us right back out of that menu. And again, now we can adjust our main amperage accordingly.
The audience can hear me now. All right. We had a question from the chat, so thank you for the chat question. Just a reminder, if you do have questions during any portion of Andrew's presentation, just put them in the chat or send that email. The question came through, is balling on the tungsten bad, or is some small ball size acceptable?
Can you repeat that question, Mike? I didn't quite hear that.
Sure. Is balling on the tungsten bad, or is some small ball size acceptable?
Sure. So that's a great question, and we actually get that quite a bit. In regards to balling the tungsten or pre-balling the tungsten, there are applications where you may want to pre-ball the tungsten. So as we talked about, the balance setting last week showed that we have the balance or the ball setting at 30%. In that, if we go into balance and turn the range all the way down, and that does give us a lot of heat on the tungsten to pre-ball that. And where that would be used is, for example, if you're doing heavy overlay applications or outside corners on thicker materials, you're going to be using a high amperage. And you want a fairly large thermal mass there to prevent the tungsten from eroding and transferring, microparticles into the actual welding pool. And so if you're doing low amperage applications, a ball, as we saw in the drawings, can negatively impact you. The arc wanders around, you don't have good arc stability. But high amperage applications, you have a lot of arc pressure from the actual arc and the amperage that's being generated and output on the torch. And so you get a natural stability from that. But you also, in many cases, more amperage, you probably want a little bit higher, a little bit larger weld anyway. You're trying to get, if you're doing an overlay, you're trying to get a little bit wider weld so you can get more material. Or if you're doing a thicker section, in many cases you want a larger weld anyway. So it's not necessarily a disadvantage, and in some cases you may want to, but for most applications, people are typically choosing a TIG welding process because it's thin materials, it's very delicate, and they're trying to get a small weld. And so that's why, for the most part, we generally recommend using that truncated tungsten, geometry, because in many cases, if they're trying to do a thick section, they probably, might have the opportunity to MIG weld it. Some cases they might not, but they might be choosing an alternative welding process if it's that thick or large of a section.
Okay, another question from the chat. This person has a Dynasty 210 and wants to know if it's possible to purchase an expansion card to access the independent EP and EN. Followed up by, are there any new feature functions on the new expansion cards versus the older ones?
So if they have a Dynasty 210 DX, so the interface that we have here tonight, that is the machine that you can get the expansion card that I referenced, and the Dynasty 210, the memory card or the expansion card that we have. There's not necessarily any different vintages of those memory cards. Once we released that option was was released regardless of the vintage of Dynasty 210 DX that they have. So as long as they have that SD memory card port, they can, and the DX interface like what we have here tonight, they can, whether it's a 210 or a 280, they can get that expansion card and activate those features.
Okay. One last question before we move on to the next topic. What was the material thickness that we're speaking about here for balling?
So generally, if you're looking at balling the tungsten, you're probably going to be 3/8 or 1/2 inch and above. Typically, if you're under 3/8 of an inch, you're going to be running more of a truncated shape versus a either a 1 diameter ball or maybe even a little bit larger diameter than your tungsten. So typically, or my personal preference is, if you're 1/4 inch or under, truncate it and truncate it to a third or maybe even a half the electrode diameter, and that's, the corners will naturally round off on their own, but you're not going to get a true like one diameter ball on the end of it.
Okay. All right.
And I think one other point there that I can't really stress enough: using the 2% seriated or the 2% lanthanated tungsten. So if you're using a pure tungsten, generally we know that those don't work well on the inverter-based power sources. They can't transfer the electrons fast enough for the switching and the AC frequencies that we're doing with these products. And the lower melting temperatures, you will get a molten end on that tungsten and have a much larger ball, so that can negatively impact you as a welder.
Okay. All right, next question. So typically, I know 100% argon is used for TIG welding, but I've been in shops and I've seen it where they actually use helium or argon helium mixture. Can you tell us why somebody would use helium and what the effects of using it would be?
Yeah, so if we think about the TIG welding process, or the true name of it, it's gas tungsten arc welding. So TIG is actually an acronym for tungsten inert gas. And back in the day when the process was first being developed, they actually used helium, or the helium shielding gas. And so you'll hear a lot of people that have been in the welding industry for a long time call it heliarc. Heliarc, TIG, gas tungsten arc welding, it's all essentially the same process, or the same base process. And so helium in itself as a gas, once that is released from the bottle and out your torch, goes into the atmosphere and floats up, and it can't be recaptured. It's in the atmosphere that we breathe and goes up to the upper parts of our atmosphere, and can't be recaptured. So there's a limited supply of it. And so over the years, alternatives have been found, and that's primarily the argon shielding gas that we use today. It's readily captured from the atmosphere that we breathe. It's able to be produced. And so when you think about a limited supply of helium, where we can't get more of it, versus a gas that we can produce and transport and utilize readily without having to worry about running out of it, it's a much more reasonable option, and in many cases it's provides the results that people are looking for. Still shields the molten weld pool, still shields our tungsten electrode. But I think where you probably see it used the most is going to be a couple different places. With my involvement with the AWS, I get to deal with a lot of people in a lot of different industries, particularly the aerospace and the spacecraft industry, which deals with a lot of military applications. And in many cases, those are old welding procedures, and old welding procedures, because of the cost and to make new welding procedures, they continue to use those old welding procedures that were developed for the use of helium. But many shops over the years, maybe they're not following a welding procedure, or they've encountered a new weld and their machine isn't capable of it. What they can do is they can use helium to somewhat stretch the legs of the machine. And what I mean by that is, if we have an argon shielding gas, and let's say it has an ionization potential of, let's just use some easy math, about 12 volts. Move this so the viewers can see this. And then we're going to say we're going to weld at about 100 amps. So we know that volts times amps equals our wattage. And wattage is essentially our heat. And so if we have a helium shielding gas, what you end up with is a higher ionization potential. So I think it's about 25%. So if you got 12 volts here, you're going to end up maybe somewhere more in the range of about 15 volts at the same amperage. Now that's all impacted, obviously, you know, to some extent by your arc length, but assuming everything else is the same, your arc length is the same, your amperage is the same, you're going to end up with about 1,200 watts of power versus about 1,500 watts of power. So if you have a welding power source that can only give you, you know, 100 amps or 200 amps, and you want to stretch and get a little bit more heat out of your machine, one way you can somewhat cheat that system is by throwing helium shielding gas. It's going to come with a price. It's definitely more expensive, and most companies try to eliminate helium from their process. But if you just have one, you know, one small batch of parts that are coming through, and you know it doesn't justify maybe purchasing a larger piece of equipment to get that extra amperage, you can somewhat cheat the system by getting you know, using the helium shielding gas, maybe buying one bottle of it and getting that little bit extra heat out of the, you know, out of the system. Like I said, it does come with a cost, and in many cases, if your process is reliant upon that, it is going to negatively impact you, because what I hear in the industry a lot is many of the companies that are using it are put on allocations. They can't get that shielding gas from the supplier on a consistent basis, or it comes, you know, at an extreme cost penalty. And so from a business standpoint, it makes it very hard to, you know, predict and control your welding costs if you don't know, can I even get the gas to do the job, or I don't know what it's going to bill at this time because there's maybe a shortage of it. And so, you know, predicting welding costs and all of that becomes a factor that has to be considered. So that's purely talking about those in the sense of, you know, a pure argon and a pure helium. What we do see is that a lot of times people will go with a blend, and they'll do like an argon at about 25%, and then helium at you know, 75%, or even, you know, flip-flop that, an argon at you know, 75% and the helium at 25%. This can affect our puddle fluidity, you know, because there's more heat into the system. That can affect our puddle fluidity. The helium shielding gas is going to give you a little bit more fluid puddle. You start doing these different blends that changes the puddle fluidity anywhere from, you know, straight argon style fluidity to a helium style fluidity. The more argon you have, the more it's going to skew towards, you know, that argon style puddle. The one thing that does benefit you, though, is arc starting, because argon has a lower, you know, arc voltage or ionization potential. It does promote arc starting at easier. So last week we talked about tungsten and using the right size tungsten to get the arc started consistently. Same thing applies here, is that if we are using an argon gas, it's easier to ionize that gas and get that arc lit. Helium, we're probably going to need to go in and maybe make some adjustments in that general setting that we referenced in last week's live stream.
Okay. Another question. So maybe I missed it, but did you talk about about why some tungsten splits and gets small bumps that form on it on the sides of the bevel?
Yeah, so essentially what's happening, if your tungsten is splitting or getting what I call crowning, or those little nodes on the end of it, is essentially your tungsten is starting to degrade and it's essentially getting overheated for the application. So if you're seeing that, you may want to consider doing that pre-balling like we talked about, or you likely need to bump up to the next size tungsten diameter for your application. Now, if you're doing short welds, you can get away with running that, you know, for a short period of time, maybe cheating the tungsten a little bit and running higher amperage than what it's designed for. But if you're doing longer welds, so, you know, over 6 inches, you're probably going to start seeing that if you're, you know, running, you know, let's say 230 amps on a 3/32 tungsten, you're going to start impacting and seeing some of that tungsten degradation. And that's an indication that you need to step up your tungsten diameter, or you're going to be going through a lot of tungsten, and likely that tungsten could be transferring into your welding pool.
Okay. One other question. There was a question about the expansion features and if they're available on the Syncrowave 300.
The Syncrowave 300, the features that we're talking about here tonight are really more of the advanced features. the sink rate product is designed more to be, a simple machine, fewer settings to, promote more from a production standpoint and throughput without bringing the confusion a lot of these, factors and functions in there. So if you're looking for these functions and understand how to utilize them appropriately, that's where it's probably time to look at stepping up into the Dynasty platform, where you can get, more of the functionality, the frequency control, extended balance ranges, the different waveforms, and then, taking it the next step further is getting, if you have like a Dynasty 210 or 280, getting the expansion card, or on the 400 and 800, that's built in, just going into the menu and activating that functionality.
Great. All right, next topic. Let's move on to DC welding for aluminum. I've seen it a few times, and it seems strange to me that somebody wouldn't just use AC for TIG welding. But why would somebody weld aluminum in DC, and what's different about it versus welding AC?
Yeah, so this is a topic that comes up from time to time, and I love talking about it. Or when, sometimes when I'm talking in, to different groups of people, it gets, I'll mention it, or I'll kind of drop the topic, that you can weld aluminum with DC, and it just kind of blows everybody's mind. There are certain applications where DC welding of aluminum can and should be done, but it does come at a disadvantage. So if we look at the different polarities that we talked about earlier, electrode negative is putting a lot of heat and generating a lot of heat into the workpiece. 70% of that heat is going down into the workpiece. Electrode positive, really the only reason why we do that is to get that oxide removal. That's the primary purpose of it and why we do it. As a welder and as an operator, trying to see and look at what we're doing, if we think about the primary purpose of having somebody involved in the welding process is to read the welding pool and to, adjust things on the fly, adjust their foot pedal, add more filler material, take away filler material, change their torch angle. But reading that welding pool is very critical in order to get good welds. And so if we're welding in straight electrode negative, what ends up happening is we lose that ability to see the welding pool with clarity. You get, we talk about you increase the balance setting, and so we reduce the amount of cleaning action. You start getting that black peppering in the weld. Well, if we start getting up 95% balance setting, we almost start seeing what happens with the welding pool. You get a lot of oxides floating on the surface of the weld. Well, you can imagine we go to 100% balance, which is straight electrode negative, or not even utilizing alternating current. What that ultimately means is that we have all of those oxides are still on the surface. None of them are being removed. And so I kind of would describe it as if you have a packet of cream cheese and you're trying to take some of that cream cheese and put it on a bagel. You want to unwrap it so you can see the cream cheese and get the cream cheese out to put on the bagel. That's essentially what we're doing in electrode or in AC or alternating current, is we're unwrapping it so we can see that material inside. If we're in straight electrode negative, it's like leaving that wrapper on. We're never going to be able to get in there and get that cream cheese to put on the bagel. And so as a welder, it's very, very difficult to know, one, where you're welding. Generally your welding puddle is going to be underneath your torch, but you don't know how large it is because you haven't unwrapped it and pulled that skin off to see where that shiny molten pool is. And so if we're trying to weld in electrode positive, it takes an extreme level of skill, and it's almost more of a feel as we're adding that filler metal into the puddle and watching that whole skin of aluminum oxides on the surface of the material move and seeing kind of where the edges of that are. It's a very, very subtle, and we're not even going to try showing it on camera tonight because it is so subtle. The cameras, wouldn't even be able to pick it up. But it has a very subtle effect on when you're adding that filler metal. The other portion of that is, we just talked about the shielding gas. generally when you're welding in an electrode negative, you need to use 100% helium shielding gas. And so, again, adding cost into what you could, maybe accomplish with a, for most applications can be done in AC with 100% argon. I did say there are certain applications you'd want to use that. If you think about, maybe like a big heat exchanger or, some sections where you have just a massive amount of aluminum. Aluminum is very, highly conductive material, so both thermally and electrically. And so when we're welding on it, if we have a large heat sink, you would either have to do some preheat to prevent it from, from soaking all the heat out of your weld right away, or you can, utilize a process like welding an electrode negative or DC welding of aluminum to drive penetration down into that part. It's going to come at an added cost for your shielding gas. It takes a much higher, level of operator or welder skill, but you might be overall saving money in the operations by eliminating hours and hours and hours of preheat to bring that big thermal mass up to temperature where you can make that weld and get the penetration that you need. So, for example, I've been into, different companies around the world, both, here in the US and in Europe, where they're building these big heat exchangers, and these heat exchangers are essentially, 8 feet by 8 feet wide, 8 feet tall, and, maybe 16 feet tall and, 120 feet long. So just almost a gigantic block of solid aluminum. There's some passageways in it, but from a welding perspective, you'd almost consider it a solid block of aluminum. And in many cases, those are, you would never be able to preheat that entire part. You'd never be able to, sit there long enough with the torch to get the penetration down into it that you would want. And so applications like that, they're going to do an incredible amount of pre-weld preparation, wire brushing, degreasing to make sure that all those hydrocarbons and as many oxides are off of that surface to give them the ability to read the puddle the best they can, and then really go by those subtle visual cues. And like I said, that feel of feeding that filler rod into the puddle and kind of knowing, where how big the puddle is and when to move and when to add and travel along with the weld to get the results that they're looking for.
Okay. Hey, we had a user submit a question about Mixtig. Can you tell us what Mixtig is?
Yeah, so Mixtig, we don't have that on our Dynasty products. We have gotten questions on this topic over the years of my involvement in both product development and product research here at Miller. And ultimately what Mixtig is, if we think about, our AC waveform, we have electrode positive, we have electrode negative, so we have our EP and our EN, and what Mixtig is it's actually mixing in portions of what I just talked about. Extended periods of electrode negative welding, and then again switching back to, if you think of this as kind of like a repeat continuous cycle, we have a couple hits of electrode of alternating current. We switch to electrode negative for a period of time, and then we switch back to alternating current. And what that does is it allows us to get, take away heat off of the tungsten and get, periods of penetration, because this is happening, you think about 120 hertz, this is happening, this cycle here is happening 120 times a second. And so if you think about how fast you're traveling as a welder and how far you're going in 1 second, you get an adequate amount of cleaning and you get all those oxides off, you can theoretically do some electrode negative and get, heat into the part without, affecting or creating that, that again, that bald portion or that tungsten degradation if you're undersized in your tungsten. What I would like to say about this is what we found through some internal testing is that we can largely accomplish the same effects of this utilizing our independent amperage that we talked about, just 5-10 minutes ago, ultimately skewing and just adding, rather than, adding an additional variable to our welding process, simply skew and add additional heat on the electronegative side. So utilizing that independent amperage, again, amperage drives penetration. This certainly would help, get more heat into the workpiece, because now you don't have these periods of time where you're putting heat up on the tungsten, but we can largely accomplish the same and get the same results without adding a new variable and more confusion for the operator, simply by using what we already have in the machines.
Got it. All right, last topic. We're doing well on time. We've got about 15 minutes left. So I've been in some shops where they are actually utilizing anodized aluminum for resistance to corrosion and other properties. Is there anything that you'd need to do differently when you're welding on anodized?
Yeah, so anodized aluminum, if we think about what anodization is, so aluminum, we use alternating current because it has that skin of oxides on the surface. Anodized aluminum is essentially a mechanical or chemical process of increasing the thickness of that oxide layer to an intended level or a predictable level, at the material manufacturer. And like you said, that's done primarily for corrosion resistance purposes. Where we see it, utilized the most, handrails. It's mostly tubing, so handrails. A lot of the boating or the pleasure boating industry, so like pontoon boat railings in many cases, different trim components on, pontoon boats or pleasure boats would be anodized. The big tuna towers or the T-tops, the center console covers and tops that you see on like center console fishing boats, a lot of those are going to be an anodized aluminum material, and it's usually what's called a BDA or bright dipped anodized. So it looks silver, so it looks like to an untrained eye, they'd probably just call it plain aluminum. But it is actually a material that's intended to be that way for like you said, the corrosion resistance purposes. In many cases, those welds, when they're putting them onto, welding two tubes together, if you're thinking about a T-top, it's going to go on a boat that's probably a couple $100,000. Those people are looking for welds that have a high level of aesthetic appearance. And so you have this really nice, BDA or bright dipped anodized tube, and then you come to the weld, and you have a weld that if you pull all those oxides out and you have these white etching zones next to it, that's susceptible to corrosion and, saltwater corrosion, things like that. Over time, that's going to give you an undesirable look. And you're going to go, well, I just paid a couple $100,000 for this boat, and now the welds are starting to look crappy. And so ultimately what I see done in the industry is most people do what's called bump welding. And so they'll use a momentary push button on the torch, and rather than a foot pedal, they'll set their amperage, and typically you're going to be 350 or so amps. It takes quite a bit of amperage, more so than what you would typically use for that material thickness. They don't typically play with the balance settings too terribly much. They're probably not playing with with independent amperage too terribly much, and it'll hopefully make sense here in just a minute. But ultimately, what they do is they use a little bit higher than normal AC frequency, so maybe up 150, 180 hertz, with a higher amperage. And what they do is what I call bump welding. So they'll if you think about MIG welding or stitch welding, where they're just taking and hitting the trigger to generate the arc, and that high frequency, high AC frequency or high output frequency, in conjunction with the high amperage, starts the weld puddle almost instantly, and actually like pushes the oxides in that oxide skin, separates it, pushes it off to the side so they can see the weld pool, melts into the base material. They'll add their filler material, and then they'll turn the arc back off. Now, that sounds like a long process, but ultimately what they're doing is they're doing hit after hit after hit, and they're using the timing of that push button, how long they're being on and how long they're pausing in between, ultimately almost like a pulser to maintain their puddle width where they want it to be and to get the, the arc width. Because a lot of times as they're coming around a joint, if it's like a tighter connection, if you think about a pipe joint where it's like a TK or Y joint where they're, down in the inside corner, it's going to be a little bit harder and take more heat to make the weld versus if they're doing on the top side or the outside, it's almost more like a butt joint. And if the fit up isn't that great, there's, variability in the joint. So they're utilizing and the amperage that's preset in conjunction with the timing of their on and off in order to maintain their puddle width and their progression along the weld. So as they start the arc, it pushes the oxides off to the side. It starts closing up. They progress forward. They hit the arc again before the puddle completely closes up, opens it back up. And so the oxides get pushed off to the side and somewhat flow back around to the back side or that back edge, the trailing edge of the weld. And so they get the that bright dipped anodized, and those oxides still flow back over the surface of the weld to somewhat protect it and give it a more cohesive weld appearance, corrosion resistance, but still having that ability to read the puddle, unlike what we talked about with welding in DC, which negatively impacts their ability to see the weld.
Complicated.
Yeah, it's definitely something that takes a bit of training and a bit of skill to learn. Not many people have the capability of doing it effectively, and those that do it, get very proficient and very good at it, and it's definitely a work of art for sure.
Yeah. All right, we got a couple more questions from the chat. Keep them coming here, and we'll try and answer as many as we can before our time is up. The first question comes: are there any upgrades or SD cards available for the Dynasty 200, or is it only for the 210?
That's a great question. So the Dynasty 200 did not have any SD or memory card port, USB port, anything like that in it in order to update the software. So that really was introduced with the Dynasty 280 platform, which is one of the first products that I launched here at Miller Electric. And then I think it was about 2015 or 2016 when we launched the Dynasty 210, and then following with the 400 and 800. That's where the SD card or that memory card port was introduced that gave us the ability to do the expansions and allow people to upgrade their products as as we developed more features and functions for them.
Okay. Another question came in was, are there any unique waveform considerations when using pulse TIG for very thin materials?
Generally, what we recommend for, and I'm assuming they're talking about thin aluminum. So the general recommendation is not to utilize pulsing with aluminum or an AC current. And I'm going to go ahead and draw some stuff here. So if we can have the screen change to the drawing board, that will help us to kind of showcase this. Ultimately, what we're looking at is, if we think about what's happening in the AC waveform, we're going from a low amperage to a high amperage in electropositive, a low amperage to a high amperage in electronegative. That switching back and forth between low and high is really what drives our arc cone to go from a wider arc cone down to a narrower arc cone. And as we talked about last week, the AC frequency, making this happen at a faster rate, will focus our arc and really tighten this arc down to this shape here that we talked about. If you start throwing pulsing into the mix here, especially if you have frequencies that match up with one another, what you may end up with is really goofy waveforms that are not predictable. Or even if you're pulse frequency and your AC frequency are offset, you might end up with a waveform, and then you'll go into the background, of the pulse, and then you'll step up for a short period of time, and you'll get these really funky looking waveforms as you go between the background amperage setting and the pulse, and then you're going through your AC waveform, and on the AC side of the machine. So typically, we don't recommend it. If you think about it from a DC application where you're welding an electrode negative and you have low amperage to a high amperage and a low amperage to a high amperage, and you're going back and forth between low and high. So this is electrode negative. This is 0 amps, and let's say 100 amps. You're going from the low amperage to the high amperage. That change from low to high is where you get that arc focusing effect from. You think about the AC waveform, you naturally have that low to high in the AC waveform. And so we can get the same effects on aluminum from our AC frequency as you do on like DC or steel or stainless steel with the pulsar and the pulse frequency. So generally, we don't recommend using the AC frequency, or we don't generally recommend pulsing in aluminum because we already get those effects naturally through that AC waveform. Hopefully that answers the question.
Yeah, I think that's a great explanation. So next question came through. Can you talk about how penetration is affected when using bump welding, the bump welding technique?
Yeah, so the penetration can be, affected. Like I said, it does take a bit of operator skill to be reading the welding puddle. You do have those periods of cooling, so if you're completely closing your weld puddle up, it can impact your ability to, effectively consume that root of the weld. If you're completely closing the weld puddle up and are not waiting for on that next hit for the weld to consume that root or that interface between the two fang surfaces. And so it does take a bit of time and a bit of expertise in order to do it effectively, but it can be done. Certainly if you're looking at getting into that, you'd want to do some sort of a welding procedure qualification, looking at how you're going about that, but it can be done effectively and is being done in the industry.
Okay. I think that's it. I don't see any more questions in the chat. So I just want to say thanks to everybody for joining us tonight for the Shop Talk Live Aluminum Series live stream event. Thanks to Andrew for walking us through all the different features and tips for advanced TIG welding. And I hope you guys found some of the content valuable tonight. Our next live stream is going to be next month at some point. Keep an eye out on our landing page for future episodes, or look for an invitation coming into your inbox. And with that, we'll say have a good evening, everybody, and I appreciate you coming and spending some time with us.